Good morning, ladies and gentlemen. Today we're going to look at a chemistry topic which is in C2 and a little bit in C6 as well, which is kind of a type of bonding really, or a variation of type of bonding, and that is polymers. So first of all, what is a polymer? So a polymer is a long chain molecule, typically covalently bonded, made from joining lots of smaller molecules together. Okay. Quick reminder though, what is this thing called a covalent bond? So hopefully you've watched another video where I went through all the types of bonding. Just to remind you, this is a dot cross diagram for the covalent bonding of water. So what you have here is you've got two hydrogen atoms and an oxygen atom. Again, remember when they bond together, the whole point is to try and get a full outer shell. They don't do it by give and take like you would in ionic bonding, it's done by the sharing of electrons. So in this case, hydrogen has one of its own electron in its outer shell. It wants to get to 2 because that would be a full shell of hydrogen, and it does that by sharing 1 with the oxygen. The oxygen's in group 6, it's got 6 in its outer shell, it wants to get to 8, and so by sharing with the hydrogen it achieves its full outer shell as well. Okay, so that's what covalent bonds are. A reminder, covalent bonds are very, very strong. Okay. Over here, slightly different picture. What we've got here is several of our water molecules, because remember, you wouldn't just have one of these things in it. You know, even in the tiniest drop of water, there would be absolutely an uncountably large number of these things. Important to remember though, these are just very small molecules, just with 3 atoms in. What holds those together is a different kind of force, which is called intermolecular forces. So the forces between molecules, that's what the word inter means, it means between. Those forces are quite weak, and this is why covalent chemicals, or simple covalent molecules, typically have very low melting and boiling points. So at room temperature, water would of course be a liquid. Lots of other covalent chemicals like oxygen and nitrogen in the air around us would be gases at room temperature. So, key question that often comes up, and we did this in the last video, why do these chemicals have low boiling points? Well, it's because intermolecular forces are very weak, so you need very little energy to basically vibrate those apart. A covalent bond though is very strong. So I'm going to do a little practical now where we're going to make a little polymer, and then we'll come back to the board and we'll talk about the properties of polymers and why they're perhaps different to the simple covalent molecules. Okay guys, so here we have a nappy. Okay, I have cut into a little bit, and the reason I've done that, if I show you, inside a nappy, as well as having this cottony wool type material, there is a crunchy material. If you've ever picked up a nappy and squidged it, you can sometimes hear it, which I can bring out, and so it's a white powder. So I've basically cut this open and collected this white powder. Okay, so this chemical is called a hydrogel. So I've collected quite a bit from this nappy. We're now going to sort of show how does that interact with liquid and therefore make our nappies work. So I'll cut away and I'll show you how that works. Okay, so here's my setup. I've got a petri dish. I've got my hydrogel. So this is the chemical that I scraped out of my nappy. So I'm going to take my hydrogel. I'm going to draw that. Let's put most of it in, shall we? Okay, so there's most of my hydrogel. So that's the chemical that's inside the nappy. So for some reason, your nappy gets wet, as happens in real life. So I'm going to start pouring on water. So remember, our water is a liquid. Observe what happens when we mix it with hydrogel. I don't see very clearly, but let's add a bit more. So it pours on, and then it becomes a transparent gel. And I can actually add a surprisingly large amount of water. In fact, let's go to pouring. And you can see that my water is very definitely not a liquid anymore. It is bonding to the hydrogel to form much longer chain molecules, which are no longer liquid at room temperature. So, and should we just see how much we can add? So, you know, you've got a very leaky child, still absorbing. And this was not all the chemical. This was actually only about half the chemical in a nappy, if that. And that just becomes this really quite funky gel. If you touch it, it is literally like Feels a bit like hair gel, might sort of that squidgy texture, which is hair gel actually has a hydrogel in it, so it's not surprising perhaps. So let's keep adding water, see if we can find the point at which it can't absorb anymore. So no, we're still very definitely solid. Look, I can almost turn it upside down, it doesn't fall out. Alright, let's go crazy then. There, I think I've reached the point now where it won't break down any further. Okay, so what have we seen there? We've seen the formation of a polymer using a hydrogel and water bonding together. Okay, let's maybe pop back to the board and see if we can explain how that works. Okay guys, so can we explain why is it when we added the water to the chemical in the nappy that the water ceased to be a liquid and became a gel, a solid in effect? So let's basically remind ourselves, water, why is water a liquid in the first place? Remember, we've got small molecules with just weak intermolecular forces between them that aren't strong enough to hold it together as a solid because those forces are quite weak. Right, over here I've kind of got a representation of what might have been happening in that gel. So my rectangular drawings here, these are representing the chemical that was in the nappies. It's called a hydrogel. Okay, so that's a polymer molecule. What happens when you put it with the water? These hydrogel molecules bond to the water, and the water bonds to more hydrogel molecules, and basically you create one very long molecule rather than lots of little ones. So you have an effect of effectively hydrogel, water forming a long chain, and there's another. So you effectively get lots of these long chains. Okay. That process is called polymerization. What we are doing is taking small molecules and joining them together to make much bigger molecules. Why did that mean now that it was effectively a solid, a gel, rather than a liquid? Well, this all comes down to how intermolecular forces work. Intermolecular forces work between any particles, there will be this weak force. The bigger the particles are, the stronger those forces get. A good analogy, if you take baked beans and spaghetti. If you open a can of baked beans, it's pretty easy to stick a spoon in and just get out a single bean. If you try and do the same with spaghetti, they tend to knot together. It's basically the same effect, but at a much smaller scale. These much longer molecules, the forces between them are stronger, and therefore they tend to stick together, because there are more places for these intermolecular forces to exist, and therefore the combined effect is that what was a weak force becomes a bit stronger. Therefore, the reason that our nappy worked, these longer molecules had strong intermolecular forces, and that was able to hold it all together as a gel. And that's why your nappy has a what's called a hydrogel molecule in there, so that when water gets in there, it acts, forms a polymer, polymerization happens, and these molecules tend to have high melting and boiling points, and therefore, in this case, turn into a solid rather than a liquid. I thought I'd show you another little experiment with polymers, just because this one's a bit of fun as well. So, different chemical this time. This chemical in here is something called sodium alginate. It's actually an extract from brown seaweed. It's a natural polymer, okay? So, at the moment, it's kind of this very sticky, can't see very clearly, my hands are the way, it's a very sticky brown liquid, okay? So, at the moment, you've got those polymer chains, and the intermolecular forces between them aren't quite enough to hold it as a solid, but it's a very, very viscous liquid, a very sticky liquid. Okay, and I've also got a calcium chloride solution. Why have I got these two things? So, effectively, what happens when I add the sodium alginate to the calcium chloride solution, the ions in that polymer switch over, so the calcium ions come out of the solution and take the place of the sodium. The chemical that makes another polymer, but this polymer has a little bit, the structure is a bit different, and therefore we get something that looks a bit different. So let me do the experiment and then we'll talk it through and see if we can work out what's happened. So here is my sodium alginate in a, try to put it in front of the camera, in a syringe ready to go. I'm going to literally just squeeze it into my beaker of calcium chloride solution, and you won't be able to see much just yet, unless you've got very good eyesight. Okay, now, something has happened in there, you probably can't see very clearly. So I am now going to just put it through a sieve. And what you might see in the bottom of my sieve, and if I pick it up it's pretty horrible, is these very squidgy little worms. We have basically made calcium alginate worms. they're quite long, and they've got a very weird squidgy texture to them. So basically, there must be something different about this polymer that means the bonds within it are strong enough to hold it together as a solid. Why is it different? So this is probably going a bit beyond what you need to know, and actually, well, I suppose not really. It's C2 polymers come up about bonding, but in C7, when we do organic chemistry, there is a whole section about polymers there, and particularly why different plastics are different. And this actually is a very similar reason. So let me pop back to my board, and I'll see if I can explain to you why this polymer is different to what I started with. Okay, so quick explanation then about how I made my calcium alginate polymer worms and why they were solid, whereas sodium alginate wasn't really. So if we think of what this looked like to begin with, sodium alginate is a polymer already, so you've got these big long chain molecules. They're held together by weak interactive forces. In this case, those forces are enough to hold it as a kind of sticky gel, not strong enough to hold it as a proper solid. How then was calcium alginate different? So if you remember, I added calcium chloride, the ions switched over, and I made this chemical called calcium alginate, which was then like a long, sticky, almost like a rubber type material. It made these little worm shapes. Difference is, when this forms, you get something called crosslinks, and in C7, we talk about this a lot more about plastics. It's one of the main reasons why some plastics are flexible, like the kind of plastic make a plastic bag out of, and other plastics like a plastic chair are much harder. In calcium alginate, it forms some crosslinks. So as well as having, so we still have these intermolecular forces, but as well as those, we actually have links, covalent bonds, between those individual chains. Obviously, if we remember, covalent bonds themselves are very strong, and therefore that means that these layers have got a proper strong force holding them together, and therefore it's much stronger. And in this case, you made a sort of a wormy sort of rubber type texture, as opposed to the much softer texture that sodium alginate had. Hopefully, we've talked quite a lot about polymers today. I haven't talked about, so my last video I did with you guys was all about bonding, so we talked about ionic bonding, covalent bonding, and metallic bonding. Polymers are obviously an example of covalent bonding, but where you have much larger molecules, and therefore you have different properties because of these much stronger interactive forces. There are some other giant structures that I'm not going to talk about in this video, but it is something you do definitely need to know about. So other examples of giant covalent structures would be things like diamond and graphite. So maybe I'll do a video on that, maybe I won't. But for today, I will probably set you a few questions. I think there are some good exam questions I can find about polymers. And I'll see you all soon, guys. Thanks for your time. Bye now.